Hello. In this video, I'm going to cover how binary file structures work via a basic overview of the Portable Executable file format. Follow the principles seen in this video, and then complex binary file formats such as JPEGs, zip files, PDFs, EXEs and DLLs, and more will be far easier to not only comprehend, but also read, modify, and even generate from scratch in your favorite programming language. Let's get started. Text files are probably the most common type of binary file that I work with. These type of files lack an enforced structure outside of limiting the byte sequences allowed. A computer only understands zeros and ones. Humans are the ones who apply meaning to those zeros and ones. For example, a bunch of folks in the 1960s, 70s, and 80s decided 0A hex, or 10 decimal, equals a new line, while 41 hex, or 65 decimal, equals an uppercase A, etc. The outcome of those early efforts became known as ASCII, much of it adopted into Unicode and used by the majority of systems today. To the computer, though, they are just bits and bytes of data. Specialized software called text editors transform bytes or sequences of bytes into human-readable characters and enable modification of text files. However, there are many files that cannot be viewed or modified in a text editor in a way that makes sense. Let's take a look at one of my favorite structured binary file formats. The Portable Executable, or PE file format, is used by Microsoft Windows to load compiled binaries such as EXEs, DLLs, system drivers, etc. into RAM and run the code found within. The PE file format itself is a bit obscure, fairly complex, and has a rich history dating back to the MS-DOS era in the 1980s. It is also mostly well documented and contains a wide variety of storage structures and is still very much a relevant file format today. There are also a number of powerful custom tools that make the format more accessible for various purposes. Combined, these things make the PE file format an arguably good choice for a video on binary file formats. The most basic tool needed is a hex viewer or editor for general purpose viewing of binary files. On Windows, I use the free portable edition of Hex Editor Neo. The best hex editors also include tools for binary file structure analysis, but those features usually cost money. There are some free general purpose binary structure parsers analyzers out there like KiTiStruct. However, in my opinion, specialized free format specific tools are the best way to dissect and analyze each specific format rather than a general purpose binary structure analyzer. For the PE file format itself, I use several such specialized tools. PEView is my go-to viewer, but I also use Puppy, CFF Explorer, Dependencies, Resource Hacker, and of course, CubicleSoft WinPE file. We also need a calculator. When working with binary files, a calculator that can rapidly convert between various bases is a must-have. While SpeedCrunch is my favorite general-purpose calculator with history capabilities, I actually prefer to use the Windows calculator when working with binary files because it does conversions more quickly between decimal, hexadecimal, octal, and binary. Next, we need a set of sample files, or artifacts, to examine. Each binary file format tends to have various edge cases, and a good artifact library will cover most of the more obscure edge cases. For example, I've created a fairly large GitHub repository of PE file artifacts that anyone can use for research purposes. Ideally, any file format you work with will have a similar artifact library available somewhere. Readable source code someone else has created for parsing a file format is also a good idea to have on hand, if only to peek at. It's very likely that someone somewhere will have had more insight into a particular area of any specific file format. GitHub is, of course, useful for finding specific keywords unique to the file format and turning up source code and related projects. Last but not least, we'll need at least one specification on the file format itself. Most binary file formats have official specifications, but some of the specifications are locked behind legal agreements. Unofficial specifications created by a community of reverse engineers can be a good starting point. Fortunately, Microsoft publishes most of the PE file format specification in the Windows API documentation. File format specifications are inevitably long, boring walls of text that get quite technical. And at this point you may wonder, what good is knowing about how a file format works? Well, if we know how a file format works, we can modify the file possibly in ways that the original designers nor anyone else ever thought to use the format for. Most of the time, we hear about the bad things people do with binary file formats, such as embedding malware. However, there are plenty of valid, legitimate, and perfectly legal reasons to modify binary files. Here are just a few positive examples of using the PE file format in ways it wasn't really intended for. We can apply changes to EXEs and DLLs to enable a newer application to run on older versions of Windows. Or to add new functionality such as patching an executable to turn it into a portable app that runs from a thumb drive on any PC. Or even to fix a bug. Microsoft is clearly okay with modifying executables in binary format because they do it themselves on occasion. And here's someone crazy enough to write a full-blown CPU emulator for older 16-bit Windows 3 programs in the new executable INE file format. INE format files won't run natively on 64-bit Intel hardware because the hardware itself no longer includes the 16-bit Intel 8086-8088 instruction set. Now that we have all of the pieces we need, let's start analyzing a PE artifact. I'll start with a hex editor to just get a feel for how raw data looks. Hex editors are useful tools for looking at the raw data of a file. Here we can see a DLL in hex editor Neo. Like most hex editors, it displays the starting file position on the left, the hex code for each byte in the middle, and an ASCII representation on the right. Most binary file formats start with what is known as a magic number or a file signature. Magic numbers are not really numbers, but a specific sequence of bytes that indicate that the file is probably in the expected format. For example, zip files start with the string pk, because the creator of the zip file format was Phil Katz, founder of PKware Incorporated. Most GIF images start with GIF89A. SQLite databases start with the string SQLite format 3. This could obviously go on for a while. In fact, there are entire tools dedicated to identifying files based on their contents rather than their file name, such as the file command on Linux. But let's get back to the PE file format. A PE file starts with a DOS-MZ signature or magic number. This is because PE files are actually made up of two separate executables, an MS-DOS executable stub and the main PE runtime. The MS-DOS stub is a leftover from the Windows 95 days when programs might include both a MS-DOS runtime and a Win32 runtime in the same executable. As far as I know, no software really ever used that feature because 32-bit programming was vastly superior to 16-bit programming. So while the DOS stub is an unnecessary appendage these days, it can be used to fingerprint the compiler and linker used to produce an EXE or DLL. Every EXE and DLL starts with a regular MS-DOS header until 3C hex bytes in. The D word, which is a fancy way of saying 32 bits or 4 bytes, at this location points to where the real INE or PE header starts. PE files store integers in little endian format, which means the lowest byte first, the highest byte last. Since Intel CPUs are little endian, the Windows loader on Intel chips rarely has to do endian transformations as it loads a PE file into RAM. Jumping to the byte in the file specified by the D word, we can see the 4-byte PE00 signature. If this were a 16-bit EXE for Windows 3, we would see a 2-byte new executable or INE signature at the location instead of a PE signature. While hex editors are mostly useful to check something specific in a binary file, it's getting a little bit difficult to follow the mess of bytes. So let's jump over to our first real tool, PEView. PEView is my favorite tool when it comes to PE file structure analysis. It's blazing fast, never crashes, keeps strictly to showing the actual structure of the PE file format, and closes file handles when it should. Unfortunately, it only works well with 32-bit PE files and has only had limited support for 64-bit PE32 plus files for the last decade. On the left side in PEView, we see a tree structure. On the right side, we see data specific to the selected portion of the tree. This tool takes care of many tedious details for us, including RVA calculations, which I'll cover in a moment. The Windows loader is responsible for loading an executable and each DLL that is referenced into RAM, mapping sections into virtual space, applying relocations, and of course checking files for validity all prior to executing a single instruction. 16-bit DOS executables, by comparison, were exceedingly simple in design. They had several major flaws in that only one executable could run at a time, with the sole exception of very fragile terminate and stay resident or TSR programs. But back in the 1980s, RAM was extremely limited and very expensive, so running just one program at a time made some sense. Also, an application crash usually meant rebooting the whole system, as DOS would get overwritten in RAM due to no separation of kernel and user space. There is also no usable mechanism to reuse code in DOS. Windows aimed to solve the code reuse problem with DLL imports, which we'll get to in a bit. PE file format EXEs and DLLs are compiled binary computer code and data that are structured in a semi-flexible way, which allows for all kinds of use cases when loading and running an executable. The goal of these semi-flexible structures is to maximize the likelihood that the Windows loader will succeed in loading each file. Now let's drill down into the first two major structures of the PE file format, PE sections and the PE optional header. First, let's look at PE sections. Each PE section is 40 bytes long and appear immediately after the PE headers. As sections are loaded into RAM, the privileges for each page of RAM is set according to the PE section's flags or characteristics. Pages can therefore be protected at load time with separate read, write, and executable permissions. Any violations of the permissions will cause a page or segmentation fault, and the OS will terminate the application. In short, having different sections is an application safety mechanism. If you want to learn more about Windows page allocations and permissions, check out the Virtual Alloc and Virtual Protect Windows APIs. Other modern OSs like Linux have similar page allocation and permission functions. Let's look at data alignment for a minute. Data alignment, sometimes called byte alignment, is making sure that the next byte of real data starts at some particular multiple of bytes. This is done by padding the data with 0 bytes out to the alignment value. Many binary files use data alignment for various reasons, but are usually structured that way for improving performance when loading the files. The alignment requirements in the PE file format are there by design due to various CPU architecture hardware requirements. Quite a few CPU architectures require code and data to be perfectly aligned just to run an application. However, some CPU architectures, like Intel CPUs, will run applications if code and data are not aligned, but will have reduced performance. While Windows plus Intel, sometimes referred to as Wintel, is the most common combination of OS and hardware for the PE file format, Microsoft has experimented with plenty of other CPUs over the years where code and data alignment are required. PE files are designed to be aligned to different boundaries, mostly for performance reasons on Intel platforms. For example, pages in the Windows OS tend to be allocated in 4 kilobyte chunks. Therefore, PE file sections tend to also be aligned to the page size of 4 kilobytes. The PE file format also makes extensive use of bit fields. Binary file format designers tend to use bit fields to help reduce the size of the file and/or improve overall application performance. Bit fields are a chunk of data, usually 1, 2, or 4 bytes long, that are sliced up into individual or chunks of bits. Each bit position represents something specific if it is turned on. Most specifications also have reserved bits that are never used for anything and should always be 0. Looking at bit fields manually is fairly slow and error-prone, so tools that map the bits to human-readable strings are quite useful here. Now let's look at the second major structure of the PE file format, the PE header. The PE header is split into the standard header and the optional header. The standard header supplies what type of machine the executable is compiled for, how many PE sections there are, the size of the optional header, and some flags. Despite the name, the PE optional header is not optional in EXEs and DLLs. The PE documentation refers to executable files as images. The PE optional header contains all kinds of pointers that describe the rest of the file. This header is also where we get our first taste of RVAs within the special PE data directory table. Despite the official Microsoft documentation saying PE data directory entries are all RVAs, they're not actually all true RVAs. While the official documentation on the PE file format is a good starting point, it is flawed by intentionally misleading readers at times and even excluding important information. At any rate, the PE data directory of general interest to most people is the import table. This table tells the Windows loader which DLLs are required by this executable, and what functions from those DLLs need to be mapped into the process space. The Windows loader is responsible for loading those DLLs as it loads the process, and those DLLs may reference other DLLs, and those DLLs may reference other DLLs, and so on. Entire tools like dependencies exist that look solely at import and export tables in executable images, which can be useful to determine what's missing on a system when the OS doesn't load a particular image. So let's find the import directory table in this file by using this RVA reference found in the PE optional header data directory. A RVA, or relative virtual address, is a number that represents a relative location in RAM that's added to the base image address. We are looking at these files from an on-the-sidelines point of view, which is an important distinction when dealing with RVAs. That is, we are looking at the raw file data on disk, while the Windows loader and the application will be looking at data and code loaded into RAM. The first step to finding the position on disk is to walk the PE section list looking for a section whose range contains the RVA value. Once the section has been found, we can calculate where on disk it sits by subtracting the base RVA to get the difference. Then we add the raw data pointer value to the difference to locate the starting position on disk. This mapping exercise is useful to show how a computer program can locate and extract information from a binary file on disk. Of course, PEView does the RVA mapping for us and also conveniently extracts the import table structures. The import directory table consists of a zero-terminated array of DLLs to import and where to put the imported addresses. The import lookup table for each referenced DLL is a zero-terminated array of ordinals or hint name RVAs of functions to import for a specific DLL. The import hint name table contains a bunch of aligned ordinals and names referenced by the import lookup table. The import address table, or IAT, contains identical data to the import lookup table until the file is loaded into RAM. When the file is loaded into RAM, the IAT is overwritten with correct addresses in the loaded DLL that points to the start of each imported function. The IAT is how Windows allows for code reuse to make applications smaller, but it can be used in other ways. For example, the IAT is regularly referenced online when dealing with remote process injection or creating executable hooks. Normally, when the executable code calls an imported function, it loads the address from the IAT and then calls that address. A hook is where an address in the IAT is ultimately replaced with another address. Then whenever the executable calls the function, it loads the address from the IAT. However, the address it loads actually points at the hooked function instead of the original function. This allows custom behavior to be created to get the application to do things that aren't normally possible. Toolkits like Microsoft Detours, EasyHook, MinHook, and even CubicleSoft WinPE files simplify the process of hooking the IAT through various means. Hooking the IAT is just one example of modifying an executable for some specific purpose. Note that the order of the import table types is not important, and import table types can even appear in different PE sections. RVAs generally allow for a lot of flexibility on where table data is stored within a file. The decision on where to place directory information within a PE file is mostly left up to the authors of compilers and linkers. While most binary file formats don't have the level of complexity that PE files have, many do have the concept of pointers that point to specific places within a file. Moving from just viewing and reading any binary file to actually modifying the file is a significant step that carries some risks. Beyond checking magic numbers at the start of the file, the Windows loader has a number of other mechanisms to make sure it is loading a valid executable image. One of those mechanisms is the PE file checksum located in the PE optional header. A checksum in a binary file can be as simple as adding the bytes up in the file to something more complex like a CRC32 or SHA256. In the case of the PE file format, the PE checksum is a slightly modified variant of the MS-DOS checksum algorithm, which just adds up bytes. It's not a particularly good choice for a checksum, and the Windows loader tends to skip checking it if its value is 0. However, the PE checksum is required to be correct and non-zero for Windows drivers and various critical files. The algorithm for the PE checksum is not included in the PE file format specification, nor anywhere else on Microsoft's website for whatever reason. Other file formats like zip files use a CRC32 to verify that the file is not corrupt. Zip file reader applications like 7-zip will usually verify a checksum before they extract the file's data. When modifying binary files, it is a good idea to update all of the related bits of information inside the file in addition to the desired change, so that the modified file remains valid when read by various software and tools in the future. Copying or backing up a binary file before modifying it is also a good idea in case the modifications corrupt the file. Well, that's the basic structure of the PE file format and how binary file formats in general are designed. We covered tools, artifact libraries, specifications, pointers to various locations within files, data alignment, data tables, checksums, and more. Even if the PE file format itself hasn't been interesting to you, binary files are just files that consist of highly organized data structures. With the relevant specification in hand and a few tools, analyzing and understanding existing binary files becomes a piece of cake. With the techniques shown here, various tools and libraries can be built to modify existing files in unique ways, and also create new files from scratch or even entirely new formats from the ground up for your specific application. Hopefully you learned something new today. Be sure to like and subscribe, and thank you for watching.